In this section, we're going to talk about one-sided limits. Look at this example, this graph. This is the graph of x over absolute value of x. So let's try to find out the meaning of this. So since we know that absolute value of x is actually x itself if x is greater or equal to 0, or this is negative x if x is less than 0. So meaning for any negative number, uh, the absolute value is negative of that number, which is eventually positive. We're going to use this definition here, but make sure that because x is on the denominator as well, so we cannot include 0. So if we don't include 0, this becomes x over x, which is 1 if x is greater than 0, x over negative x, which is negative 1 if x is less than 0. That's why the graph of this function is 1 on the right side of the 0 and negative 1 on the left side of the 0. So when we approach to 0, when x approaches to 0 from the right side, meaning when x is coming from right side towards 0, the value of the function is coming from this graph on the top. And when x is approaching to 0 from the left side, the value of the function is coming from this graph. So it has different limits. Limits means the value of the function when x approaches to 0 from left side and from right side, it has two different values. Okay, so different right hand and left hand limits at the origin. Look at this graph here. When x approaches to 0 from the left side, meaning when x approaches to c, when x approaches to not 0, c, here is the c. When x approaches to c from the right side, this is right side to the c, we write down plus sign here. So x is approaching to c from the right side. Instead of saying right side, we can write down plus. This plus is for right side. Okay, so when x approaches to c from the right direction, the value of this function, as you can see that it's approaching to this value, which is L. So that is called right hand limit of the function f of x when x approaches to c from the right side. Look at another example here. Here x is approaching to c from the left side. So instead of saying the left side, we just write down x is approaching to c minus. This minus means from the left side. Okay, so left hand limit as x approaches a c. I should write down this here. Left hand limit as x approaches to c. Okay, so these are two examples. So the way we define limit in our previous section, we can do the same thing for the right hand limit and the left hand limit. So definition: assume the domain of the function f contains an interval cd to the right of c. We say that the function has the right hand limit L at c and right. The limit of the function f of x when x approaches to c from the right side is L. If you want to go back to this graph here, there is nothing on the left side of the c. So the domain of this function is starting from c. So as you can see that the domain of the function starts from c and then anything else on the right side. So in that case, there is a right hand limit. And then if you go back to the previous section and think about the epsilon delta definition, precise definition of the limit, we can apply the very same thing here even for the right hand limit. Okay, so this is the precise definition. Same thing goes to left hand limit. So for the left hand limit, you don't have anything to the right of that c. For this, you have to look at this graph. After c, there is nothing. So the domain is starting from some number and goes up to c. Okay, and then we can use the precise definition of the limit for the left hand limit as well. This theorem is very important theorem. There it gives you very important relation, and it says, suppose that a function f is defined on an open interval containing c is just a value, except perhaps at c itself, then function has a limit as x approaches c if and only if it has left hand limit and then right hand limits there, and these one-sided limits are equal. So this is the left hand limit and this is the right hand limit, and they are called one-sided limit. And we can say the function has limit. This is just a limit. Function has a limit when x approaches to c is equal to L. That is only possible if that function has a left hand limit then right hand limit and both of them are equal. Okay, so this is if and only if function has a limit, that means function has a left hand limit and right hand limit and they are equal to the limit. If function has the left hand limit and then right hand limit, and if they are equal, only in that case the limit of the function exists. Example here, this is a graph and we are trying to find out, let's say this is the graph of the function f of x. What happens when x approaches to 3? So when x approaches to 3, 3 is here. From the left side, when x is approaching to the 3 from the left side, this is how you write. When x approaches to 3 from the left side, the value of the graph is going towards 0. And when x approaches to 3 from the right side, this is the right side, the value of the function goes to 3. Though the value of the function itself has a value 9, as you can see here. So here this value is 0 and this value is also 0. So when x approaches to 3 from the left side or the right side, the graph is going towards 0. That's why the left hand limit is 0 and the right hand limit is 0. So based on this information, now we can say that because the left hand limit and right hand limit, they are equal, so left hand limit of this function and then right hand limit of same function when x approaches to 3, both of them are equal, which is 0. So based on this theorem we can say that because they are same, the limit of the function should be the same. So does limit of the function exist? Yes, it does. And why? Because the left hand limit and right hand limit, they exist and both of them are equal 0. Okay, then what is the limit? The limit itself is 0. Let's look at this example here. As I mentioned earlier, the definition of absolute value, we can use the same trick here. uh, the absolute value of x plus 7 over parenthesis x plus 7. So this is actually, absolute value of x plus 7 over x plus 7 is actually, if x plus 7 is greater than 0, then this value on the top is x plus 7 itself, and there is x plus 7 on the denominator, so you can cancel it. And if x plus 7 is less than 0, this value on the top would be negative of x plus 7 over x plus 7. If you cancel it, it gives you negative 1. At 0, when x plus 7 is 0, this function is undefined, so we don't have any value. So this is the same example like we did here first time here. This is the same thing. The absolute value of x plus 7 over x plus 7 is either 1 when x plus 7 is greater than 0, which means when x is greater than negative 7, and negative 1 when x is less than negative 7. If you try to plot the graph of this function here, so negative 7 is somewhere here. So let's say negative 1, 2, 3, 4, 5, 6, 7. So negative 7 is here. So this function would be 1 when x is greater than negative 7. So 1. So let's say this is 1. Let's say this is negative 1. this function is 1 when x is greater than -7 and -1 when x is less than -7. So by using this graph we can say that when x approaches to -7, when x approaches to -7 from right side, the graph, as you can see that the value of the function approaches to 1. So this will be 1. And when x approaches to -7 from the left side, the value of the function using this graph approaches to -1. So that's why this will be -1. There is one theorem, it says, the limit of sine theta over theta when theta approaches to 0 is 1. Theta is in radian. This theorem is always true no matter what theta you have here. For example, let's say instead of theta you might have sine something over the very same thing. When that same thing is that value inside this box approaching to 0, that will be 1. So instead of theta you might replace this theta by some box, and if that box is approaching to 0, then sine of that box over that box, the value inside the box is equal to 1. We're going to see one example here. Here is a tangent for x over x. Okay, so we know that tangent means it's actually sine 4x over cosine 4x over x. So I can rewrite this problem because we need to use this relation. So I can rewrite this problem as sine 4x over 4x, and I need to balance this 4, so I'm going to just put 4 here, cosine 4x. So I can cancel this 4 and 4. So when x approaches to 0, this 4x is also approach to 0. So meaning I can apply this limit function to both of this the fractions. So I can write it down, limit x approaches to 0 sine 4x over 4x times limit x approaches to 0, and that is possible because of the the limit of the product is equal to the product of the limit if both of the limit exist. That's the property of the limit. So as you can see that when x approaches to 0, we can also write down the 4x approaches to 0. So now you can see that when 4x approaches to 0, this expression approaches to 1. You remember this box? I'm just putting 4x here. So when 4x approaches to 0, sine 4x over 4x gives you 1. So when 4x approaches to 0, sine 4x over 4x, that value would be 1. Now for this part, we don't have any problem on the top. That's a finite number. When x approaches to 0, the cosine function 4 times x also approaches to 0. So cosine 0 is 1. So when x approaches to 0, this limit would be 4. So the answer for this problem is 4. Okay, so that's one-sided limit.